Hello everyone, this is the video for section 12.4, which is called Area of Parallelograms and Other Polygons, which is really an awful title because pretty much this section only looks at one other polygon, trapezoids. A lot of the ideas, I suppose, in this section, in the previous two sections, could probably be applied to where we could find the area of just about any other polygon. That we're going to reasonably be looking at in this class, but for whatever reason, I don't know why, the book just says and other polygons. So anyway, either way, have a look as always the previous sections because we're going to need a lot of what we've looked at for this section. But let's get started. So we're going to be looking at parallelograms, which is a natural extension of looking at rectangles because every rectangle is a parallelogram. Now, not every parallelogram is a rectangle. So you may want to go back and review the properties of a rectangle and the properties of a parallelogram. But just as a quick review, you hopefully remember that a parallelogram, the opposite sides are going to be parallel. There's some other properties about the angles that, the adjacent angles are supplementary and opposite angles are congruent. But for the most part, all we're going to be concerned about is that the opposite sides, that the pair of opposite sides are always going to be parallel to each other. Now, if they're parallel and we contain all right angles, every parallelogram that contains a right angle or right angles is going to be a rectangle. So we have that special case. So a lot of the ideas of what we talked about with rectangles are still going to apply to parallelograms. And we'll see in the next section how essentially from an area standpoint, rectangles and parallelograms are the same shape. But we'll talk about that more in the next section. So quick definitions, we've got that the base of the parallelogram could be any of the four sides. So I'm going to draw sort of a very rough generic parallelogram. When I hear parallelogram, I think of a shape roughly like this. So any of these four sides could be the base. Just for convenience, I'm going to make this one the base along here. And now, if this is my base, the height of the parallelogram has to be a line segment, so it's going to have definite length to it, and it has to be perpendicular to the base, and it has to connect a point on the line containing the base to a vertex not used by the base. So this is the reason why we're going through this. So really, I've got two vertices that I'm not using as part of the base. Either one of these could work. So I could drop this down to the base along the perpendicular, and this could be my height. Or I could drop from this vertex down, and then this is why this is important, the line containing the base. Because this is not going to hit the base, but it will hit the line containing the base. And so just like we talked about with triangles, we can have this height that is external to the shape. It still meets all the conditions. It's still at a right angle. That's a right angle symbol. The only difference is, unlike this height, which actually hits the base, this height will only hit the line that contains the base. Not a huge distinction. Both of these will work, and then we'll see later on, we don't even have to use necessarily a vertex. We could use any point on this opposite side and drop it down, and that'll make a height as well. But for being consistent with the book's definition, we're just going to talk about this from this vertex down to this line. So the way the book defines it, I didn't think it was entirely clear or obvious, so I wanted to kind of walk through an example of this relationship between base and height, like we talked about with triangles. Understanding what the base and the height are and their relationship to each other is crucial and fundamental to being able to talk about, understand, and teach this approach to finding the area of a parallelogram. So I want to make sure we talked about those two things, those two ideas, the base and height. So this picture should be familiar. I found this online and I used it in one of the previous sections. So we can talk about this a little bit more about what's going on in this figure. So one way of finding the area of the parallelogram would be to use this movement principle that we've talked about before. and taking this triangle and moving it over here. I'm not sure what happened there. So moving it into this space so it fills in this amount, and so then we get this rectangle. And so we can see that once we've defined the base and height of the parallelogram, the area of the parallelogram is just going to be the base and the height, which is the same formula that we had for the rectangle. Again, knowing the formula is one level of understanding, but why is the same formula for a parallelogram and a rectangle? That's the more crucial thing. I really want you to understand why it's the same formula. And so we can see here by this movement principle how we can take these parallelograms and essentially convert them into rectangles. The base and the height stay the same. Take a moment to convince yourself that this length B is the same as this length B. I've talked about it in a previous slide, but so make sure that you're convinced. The height stays the same. That's obvious because that segment hasn't moved or changed, but that B has been sort of rearranged. The longer part has gone from being on the left to being on the right, but we're still adding together the same two segments, so the sum of their length should be constant. But this is going to be our area of the parallelogram and how to show it using this movement principle. Now, another way that we could show the area of this parallelogram is by using the sort of takeaway method that we talked about before in class. And so one way that I could do it would be to put these vertices in and then drop this down and over, drop this down and over. And so now I've got my big rectangle, which measures 1, 2, 3, 4, 5, 6. And so so the area of my rectangle is 6 by 4, which is 24 square units. And so this is my big rectangle. So I know the area of my parallelogram has to be less than 24 units. Now, one way that I could take off the area that I don't need is I could find the area of these two triangles. So this would be 1/2 of 1 times 4. So I know each of these is 2. So that certainly works. But another way that I could do it would be to move this part over here because I'm going to have these matching pieces. And so then when I join these two together, I've got the total is going to be 1, 2, 3, 4. It's not a huge difference. I mean, it's the difference between doing 2 2s or 1 4. So I mean, obvious is it's numerically it's the same thing, but conceptually it's very different. In one case, I'm finding the area of two different triangles, and in one case, I'm putting the two triangles together to make them into a rectangle and finding just that one area. Finding the one area in a lot of ways is easier because you're just finding one area, but is also maybe conceptually more difficult because students have to understand this idea of putting these two triangles together to make that rectangle. Keeping it separate as two different triangles is going to be a little bit easier because we're not combining any shapes, moving anything around or combining anything. But I got to do two things instead of one. Hopefully, if students do the two triangles separately, they start to notice, hey, the area of those two triangles is always the same. Why is that? And then that is a good sort of launching point for this conversation about the fact that these two triangles are congruent. They're the same shape and the same size and have the same area. And so rather than doing area plus area of the same, that leads us into 2 times that area, which then leads us to just combining them together into one rectangle. So even if students would rather do the two triangles, the discussion in class should lead us toward students being able to see that they could combine it into one rectangle even if they don't want to. The other shape that is kind of mentioned in this section, and it's strange because it's really only mentioned in the problems. It's not really mentioned in the text, but problem 4 talks about trapezoids. And so rather than sort of wait for people to get to the problem in the homework and not be too sure about it, I wanted to talk about it kind of briefly in the video. So 2 different ways we could think about doing it. And so one way would be this subdivision method. So I could drop this line down here, and so now I've got this rectangle which is 10 by 7. So I've got this rectangle here, which is 10 by 7. And so I know that's going to be 70 square units. Now, this part over here is going to be a little bit harder to figure out because students are going to be kind of curious, well, what's this length? And then what's this length? And the reality is, we don't know those individual lengths. We just don't. But we do know the sum of those lengths. So one way to talk about this problem would be to take this rectangle and sort of remove it. We're just going to pull it out of this trapezoid. And now those two triangles are going to collapse on each other, and they're going to form a triangle that's going to look kind of like this. So this is the trapezoid with the rectangle removed. And so I don't know what this length is, I don't know what this length is, but I do know that together they add up to 14. And this height is still 7. And so we can see here that this 7 and this 7 are going to fit together nicely, and that's going to stay a 7. And so now the rectangle, we said was 70. And now the area of the triangle is going to be 1/2 7 times 14, which is 49. And so I know my total area is going to be 119 units square. That's the area of my trapezoid. So this is one way of solving this problem, taking this rectangle out, putting those two triangles together, and then finding the area of that sort of combined triangle, and then doing this by addition. So the other method is we're going to be using the takeaway method that we've talked about before. A lot of the principle is the same. I'm going to enclose my shape into a rectangle like this. And I'm going to kind of shade this stuff in red because this is the extra area that we want to get rid of somehow eventually. So my big rectangle, I know, is 7 by 24. And so I can find the area. And the area of that rectangle, so the area of the big rectangle is going to be 168. That's what I got. 168 units squared. Okay. So now the same sort of idea. I need to find these areas. But again, if I couldn't find this length before, I certainly can't find it now either. So I don't know these individual lengths, but I do know the lengths if I combine them together. So I do know that these two combined are still 14. So I can take this triangle and move it over here like this. And now I know that this whole thing is still going to be 14. And so this 14 by 7 triangle is going to be an area. So here, let's go back to the area of my, and I'll draw it in red so we can make the distinction. The area of this red triangle now is going to be 1/2 7 by 14. Again, it's the same idea from before. I don't know this individual length. I don't know this individual length, but I do know that combined they're 14 units. This height stays the same as 7 units, so this area is still 49 units squared. And then if I subtract the 168 minus the 49, then I still get my 119 units squared as the area of my trapezoid. Not a huge difference between these two methods. In both cases, we're still combining two triangles where we don't know the length of the base to get one big triangle where we do know the length of the base. It's operationally very similar, but conceptually very different. In one case, we're breaking it into 3 parts and adding those parts together. In this method, we're making it into one big part, this one big rectangle, and then subtracting off the parts that we don't know. So one is this subdivision approach and one is this takeaway approach. Answer is the same, which we would expect, but conceptually very different. So for your checkpoint problem, here's a parallelogram. And so I want you to try to find the area of the parallelogram. As some bonus fun, if you want, you can find the perimeter of the parallelogram as well. But for right now, I just want you to try to find the area. So a little bit trickier because of the way that it's presented. I won't say much more than that. If you have any questions about this problem or anything else from the video, as always, please bring your question to class and we'll get it answered. All right, thanks.